Hello. In this last part of the talk, I'm going to talk a little bit more in detail how our main results can be used in the analysis of concrete PDE models. Then I'm also going to explain the abstract framework that our result employs and formulate our result mathematically. I'll also sketch the main steps of the proof. To illustrate the use of our results, let's consider quite a simple coupled PDE system, a so-called wave heat system consisting of two one-dimensional PDE models, a wave equation on the first line. So here the subscripts denote the partial derivatives with respect to the two variables, and then a heat equation. The wave equation lives on the interval from -1 to 0, and then correspondingly the heat equation, the spatial domain of the heat equation is the interval from 0 to 1. And at the endpoints of the intervals, at -1 we impose a Neumann boundary condition for the wave equation, and at the other end, at point 1, we impose a Dirichlet boundary condition for the heat equation. And the most interesting part of the boundary of the domains are at the point 0, where the two spatial domains meet and the two differential equations communicate with each other. And this communication is described by the boundary conditions that couple the two equations. And these boundary conditions require specifically that the slopes of the wave profile and the heat profile at the point 0 match, and that the velocity of the wave equation at point 0 is equal to the temperature of the heat equation. And for this model, we're interested in describing the decay of energy of the solutions as t goes to infinity. And the total energy of the solutions can be described as the total energy of the wave equation, consisting of the kinetic energy and the potential energy of the wave, plus then the thermal energy of the heat equation. And in order to use our approach to study the energy decay, we would like to decouple this coupled PDE into two systems. One which has unstable dynamics, and the other one which has more stable dynamics, and which then communicate in a feedback loop through an exchange of signals. And in this situation, for our model, we can define system 1 to be the wave equation defined on the first line, and system 2 we define to be the heat equation. And then the exchange of signals of the or between the two systems is determined by these two coupling conditions. So what we want to do at this point is to equip both the wave equation and the heat equation with suitable inputs and outputs in such a way that when we implement this feedback interconnection between the two systems, then we recover the original boundary conditions and our original system. And in this particular situation, the decoupling can be done in the way shown here. So for the system 1, we define this indeed to be the wave equation, and the input of the system we define to be a boundary condition of the equation at the point 0, which determines the value of the velocity of the wave profile at this point based on an external signal, an input to the system. Correspondingly, we define the output of this system to be a measurement of the deflection of the wave profile at the point 0. And for the heat equation, which makes up system 2, we similarly define an input and an output. The input again determines a boundary value of the heat equation at the point 0, this time a Neumann trace based on an external signal, which is the input of the system, and then the output of the system is the evaluation of the temperature at this point 0. And then the kind of feedback interconnection we are interested in implementing is where we assign the input of system 1 to be the output of system 2, and then the input of system 2 to be the output of system 1, but with the flipped sign. And with these choices of inputs and outputs for our two systems, this interconnection becomes exactly the pair of boundary conditions in our original model. So because of this decomposition shown here is an appropriate one for our analysis. Then we can recall what we needed to know about our two systems to use our results. First of all, we wanted to know that our two systems are impedance passive in the sense that they have no internal sources of energy. And then there are also some conditions on inputs and how the inputs and outputs affect the system. I'm not going to go into details regarding this, but I'll just mention that these conditions are satisfied for both of our systems, the wave and heat part, and because of this, again, we can use this decomposition. Then we wanted to know that system 1, the unstable system, becomes stable when we apply this negative feedback where we take the output of the system itself and feed it back into the input of the system with a flipped sign. And then we would also like to know an estimate for the decay rate of this energy in this stabilized system. And finally, we also wanted to know something about the transfer function of system 2, which is in our case the heat equation. If we start with the assumption on the wave system, we can investigate how the system behaves when we implement this negative feedback. So what we want to do is we want to assign U1 to be equal to the output Y1, but with a inverse sign. And what this amounts to is a modified boundary condition for the wave equation at point 0. And this boundary condition, in fact, has an interpretation as a boundary damping in the wave equation. And this kind of a wave equation is understood very well, and in particular, this system is stable in such a way that the energy of all the solutions of the equation decay at a uniform exponential rate. So from the wave part of our system, our conditions are satisfied. And then for the heat part, we are interested in finding the transfer function, which gives us a map from the Laplace transforms of the input of the system to the Laplace transforms of the output. And we can do this by taking a formal Laplace transform of our heat equation here. And in this transformation, the time variable is replaced by a frequency parameter lambda, and then the time differentiation is replaced by multiplication with the lambda parameter. And with this transformation, the three first lines of our equation become a boundary value problem which is parameterized by the parameter lambda. And this is quite a simple system that we can solve even by hand. And when we obtain the function w hat, which is a function of xi, and then the last line tells us how the Laplace transform of y is obtained as a boundary trace. When we complete these computations, we get an explicit form of the transfer function. And this is now possible because our heat equation is quite a simple system. Normally we would maybe have a little bit more indirect information of the transfer function. But now that we have an explicit formula, we can gain all the necessary information about the behavior of this transfer function. And in our analysis, the relevant part is a lower bound for the real parts of this transfer function along the imaginary axis. Now we can see that this lower bound is not uniform in the sense that for higher frequencies the lower bound is smaller, but that is completely fine and even expected in our analysis. Putting all of this information together, we arrive at our main result, which says that we do have, for our wave heat system, decay of energy of all classical solutions as t goes to infinity, and then we get a nice rational decay rate for the solutions, and it's even possible to show for this model that this decay is optimal. Okay, next I want to talk a little bit more about the mathematical formulation of our main result. So in order to analyze a wider class of partial differential equation models, our result is posed for infinite dimensional differential equations on Hilbert spaces. So instead of considering particular PDEs, we consider systems which are ordinary differential equations but on infinite dimensional vector spaces. And in the case of particular coupled PDE models, these two systems describe and can be used to represent the two PDE models that are involved in the coupling. In the setting of analysis of coupled partial differential equations, the spaces where our systems live are usually function spaces like the L2 space, and then the operators A1 and A2 are suitable differential operators which describe the spatial derivatives in the equations. And then the operators B1 and B2 describe how the inputs of our systems affect the behavior of the differential equation. And then finally, B1 also describes how the measurement of the output of the system depends on the solution or state x1 of the differential equation. More generally, it could be possible that we would have another operator here instead of this B1, but in the context of the types of models that we consider, it's usually the case that the operator here really is an adjoint of this operator B1 in some sense. But let's illustrate this, the types of models we're interested in, with a practical example. If we continue the analysis of the wave heat system, we can see how our heat equation part of the model looks like as an abstract system of this form. So if we start with the internal dynamics of the heat equation, if we want to represent this as an infinite dimensional differential equation, we would define the state of our system in such a way that at each time t, x2t is the function which determines the temperature profile at time t. And this gives us this kind of a infinite dimensional differential equation when we choose A2 to be the second order differential operator with respect to the spatial variable. On the other hand, the measurement of our system is the temperature, or the output of our system is the temperature at time 0, and for this purpose we would choose y2 to be simply the boundary trace of this function at the point 0. And in this example, describing how the inputs are affected by the inputs affect the behavior of the infinite dimensional system, and finding the operator B2 is a little bit more complicated, and I won't go into details here, but I'll just mention that this is also possible. For the wave part then, we can do the same, but maybe the main difference here is that because the wave equation is a second order differential equation with respect to time, and we want to represent it as a first order in time differential equation, then we can consider an extended state variable where we consider both the deflection profile of the wave at time t as well as the velocity profile. And with this modification, it's possible to also formulate the wave equation as in this form shown here. So for these two abstract differential equations, our interest is then to investigate what happens to the energy when we couple these two systems together in a feedback loop. And the feedback interconnection we're interested is again that we assign U1 to be the output of the system 2 and the vice versa, but with a flipped sign. So when we take our the first part of our coupling, we assign U1 here in the first equation to be equal to the U1, the output of system 2, which is B2 star X2. And with this we get the first line of our differential equation shown here. And similarly we assign U2 in the second equation to be the output of the first equation, but with a minus sign, to arrive at the second line of the equation shown here. And with this process we arrive at this composite differential equation on a product space where the main operator, this equation no longer has any inputs or outputs, and the main operator has this block form. And when we investigate the energy decay of the system, in the context of our models, the energy is usually proportional to the square of the norm of this of the solution of this differential equation. So we can simply equivalently consider the convergence of the solutions of this equation. As stated before, the basis of our investigation of the decay of energy is on the knowledge of the impedance passivity of our systems, behavior of system 1 under this negative feedback, as well as the transfer function of system 2. And impedance passivity in the setting that I'm presenting here is in fact guaranteed by a relatively simple condition that the operators A1 and A2 should be dissipative. This condition requires that if we take the inner product of A1x with x, then the real parts of this inner product should always be non-positive. And dissipativity is a condition which is a very useful one and very well understood in the setting of abstract differential equations, and this leads to very nice theory for us as well. One of the key background results in the analysis of the stability properties of our abstract differential equations is that we can in fact describe the convergence of the classical solutions of this equation by the growth and bounds of the resolvent operator of this main operator A. So in order to investigate the decay of solutions of this equation as time goes to infinity, it's sufficient to find a bound for is minus a inverse on the imaginary axis. More precisely, this result says that if this resolvent norm is uniformly bounded on the imaginary axis, then we get uniform exponential decay of all solutions of the equation, where the exponent alpha doesn't depend on the choice of the solution. We saw already in our examples that we often don't get exponential decay for our models, but instead a slower decay. And this situation is described in the following, in the second part of the result, which says that if the resolvent norm can grow on the imaginary axis, but is bounded by a polynomial, then we in fact get rational decay of energy of the solutions. And here the decay rate for the solutions of the equation is in a direct relationship with the growth bound of the resolvent on the imaginary axis. And this result, the first part of this result, is quite classical and dates back to the 1970s and 1980s. And the second part of the result describing the rational decay of energy is much more recent, and it was shown in 2010. So this result converts our analysis to the estimation of the resolvent operator for this coupled or this composite operator here. And this estimation we want to do based on the knowledge of behavior of system 1 and system 2. From system 1, we will use the information about the resolvent of A1 minus B1 star, because this is in fact exactly the system operator we get when we apply the negative feedback to system 1. And because of our previous result, this resolvent norm describes the decay of energy in system 1. On the other hand, the transfer function of system 2 in fact has a very concrete formula based on the resolvent operator of A2 as well as the operator B2. And this leads to our main result. We assume that system 2 is stable in the sense that the resolvent norm of A2 is uniformly bounded on the imaginary axis. And from the transfer function of system 2, we assume that the real parts of this transfer function are bounded from below by positive numbers on the imaginary axis in this sense shown here. If P2 is a scalar valued function, this just simply leads to the lower boundedness by positive numbers of the real parts, but this condition also works for vector valued functions. And I could also note that the impedance passivity of these systems already imply that these real parts of the inner products are always non-negative, and because of this, the additional assumption here is the positivity of these values. And the eta here is a function which is allowed to go to 0 as s goes to in plus or minus infinity. And under these assumptions, our result states that the resolvent norm of our coupled system is bounded by a constant times the resolvent norm associated to system 1 under negative feedback divided by this function eta. And this achieves our goal indeed in describing the stability properties of the coupled system in terms of system 1 and system 2. And here we note that if we have better stability properties of the system 1 under negative feedback, this leads to relatively better stability properties also in our system, coupled system. And correspondingly, if the real parts of the transfer function of system 2 decay fast as s goes to infinity, this leads to weakening of the stability properties because of this bound becoming larger. Okay, and in the last part of the talk I want to sketch the main steps of the proof of this result as well. This proof consists of three main steps. First of all, we are interested in the resolvent operator and the inverse of is minus a when a is this kind of a block operator matrix. And for this we will use the Schur complement analysis. And then in the second part, in analyzing the Schur complement, we do like a nice addition and subtraction of a term that helps us a lot in the analysis. And finally, we will employ a dissipativity argument in the estimation of the Schur complement. And I want to repeat that our result is posed for an infinite dimensional system where A1, A2, B1, B2 are all operators which may be unbounded. But in following the proof, it's also completely okay to just think of these as matrices if it helps you follow the arguments. So, starting with the analysis of for the analysis of the resolvent, we note that because we have this block structure also for is minus a, we can employ the Schur complements in the analysis of its invertibility. And for this purpose, we can write IS in this composite form consisting of three block operators. Here we denote R2 as the resolvent of A2 for brevity, and this resolvent we know by assumption to exist and to be uniformly bounded on the imaginary axis. And here the outer two triangular block operators are invertible, and similarly IS minus A2 in the diagonal block operator is invertible. Because of this, the invertibility of IS minus A is determined by the invertibility of this Schur complement S here. And S in our case has a very specific form, which consists of IS minus A1, and in addition this term which involves all the three other operators in our block operator. And here we can note that the middle part of this last term is in fact exactly the transfer function of system 2. And this is nice because we post assumptions on P2, so this gives us an opportunity to use those assumptions as well. And as I noted, the resolvent of IS minus A2 is uniformly bounded on the imaginary axis, so the inverses of the first and the last triangular operators are also uniformly bounded, as well as this term in the diagonal block. And this also leads to the situation that the resolvent norm of A is bounded by a constant times the norm of the inverse of S on the imaginary axis. So what we really want to do now is to estimate this inverse. And for this purpose, we will show that on the imaginary axis, S is bounded from below. And in order to get the result in our claim, we would like to show that if we let y to be S applied to x, then we would like to show that the norm of x is bounded by a constant times these coefficients relating to the transfer function of S2 and the system 1 under the resolvent of system 1 under negative feedback times the norm of y. In order to achieve this, what we can note is that since y is equal to s times x, we can, in this formula, add and subtract a term which has this b1 star x to get a modification of the first two terms to change these into the resolvent of system 1 under negative feedback. And what we need to do to compensate is to also add another term which cancels the first term in the second equation, but this is completely fine. And now that we have assumed that this first term, this first operator here is boundedly invertible on the imaginary axis, we can, from this formula, solve for x from here. And this gives us a formula for the x in terms of the resolvent of system 1 on the feedback and other terms. The downside of this formula is that it's implicit in the sense that on the right hand side we still have x as well, but we can try to deal with this a bit later. And if we denote for brevity the resolvent of system 1 under negative feedback by m1, then this formula and the fact that the norm of P2 is uniformly bounded on the imaginary axis gives us our first estimate for the norm of x. So the first term looks very good because we just have m1 and the norm of y. And in the second term, we have something relating to the norm of the system 1, the resolvent of system 1 on the feedback, and also this term which is the b1 star x norm. And as I mentioned, the first term looks very good. It's missing the function eta s, but that's just an improvement. But the second term is something that we still need to estimate. But in estimating the norm of b1 star x, we will employ the dissipativity of the operators that we have assumed. And more precisely, because we know that by our choice y is equal to the Schur complement applied to x, we can simply see what happens if we take an inner product between y and x and compute its real part. So substituting here for the formula for y, we generate three terms. The first term is obviously an imaginary number, so that's why its real part is equal to 0. In the second term, we encounter a real part of this inner product, which was exactly part of the definition of the dissipativity of the operator A. So because the real part is always non-positive, we can estimate this term from below by 0 to arrive at a formula which only involves the last third term in our inner product. And here we can employ our assumption on the transfer functions P2, which said that exactly these kinds of inner products should be bounded from below by the function eta at s, as well as the norm of the quantity that we have here. So this gives us lower bound for these real parts based on eta and the norm of b1 star x. And this we can turn into an estimate of b1 star x norm, because the real parts by Cauchy-Schwarz are can be estimated by the norms of x and y. And now this information gives this estimate gives us information about one of the terms in our estimate here. And in fact, using this estimate, because together with the Young's inequality in a suitable way, gives us an improved estimate for the norm of x, where we have been able to remove the x from the right-hand side of the equation. The downside of this process is that Young's inequality increases the powers of the rest of the terms here on the right-hand side. So this term, which used to look very nice, now has a second power. And indeed, but otherwise this eta s is exactly of the form that we would like. And this situation doesn't necessarily look very good, because it would seem that if we do a naive estimate here and estimate the resolvent norm of this term by m1, then we get an estimate of the form that we roughly like, but with m1 to the power 2. And this is in fact a suboptimal estimate. And the reason for this is that the dissipativity implies that in fact the resolvent norm of exactly this kind of a minus bb star behaves better when it's applied to the operator b compared to what how the resolvent norm behaves by itself. So a dissipativity argument can in fact be used to show that this, even though we have this second power in the resolvent norm in the second estimate here, this is in fact exactly bounded from above by m1. And this leads finally to the estimate that we're looking for, where the norm of x is bounded by m1 over eta times norm of y. And this completes the proof. So to recap, the proof of our result showed that if we have an estimate for the lower bound of the transfer function of of the system 2 on the imaginary axis, then the resolvent of the coupled system can be bounded by the resolvent of system 1 under negative feedback and this eta s. And the proof consisted of these three parts, where we first employed the Schur complements to analyze the inverse of the block operator matrix. And then we had this adding and subtracting of suitable terms to introduce the resolvent of the system 1 under negative feedback. And finally, we had used a dissipativity argument in order to estimate some parts of the resulting expressions.